Thank you, Peter. I hope you can all hear me and see the slides. So this part is about the theory of surrogate explainers. We'll cover briefly text, images, and then dive into tabular data. For all of them, we'll explore interpretable data representations, data sampling, and explanation generation. But before that, I want to talk briefly about the concept of explainability in artificial intelligence, and also talk generally about surrogates, not only in AI. So what is explainability? Well, we all work on it, but there is no universally accepted definition. Some that you can find and that are often argued in favor of is simulatability, which is the ability of the explainee, the person to whom you deliver the explanations, to actually simulate the black box process that you're trying to explain. And the argument goes that, well, if the person can replicate the behavior of a black box for, say, an individual data point. So you give a data point to a person, and then the person can either in their mind or with a piece of paper and a pencil go through some steps and derive the prediction of the would-be black box. Then some people argue this is explainable. Well, there are also arguments which predate this particular one that says this is not entirely the case. And the main argument is the Chinese room theorem, which says if you have a person locked in a room with a bunch of books that prescribe how to translate English into Chinese says, and on one side this person gets a piece of paper with a sentence in English, and by using these books without having any working understanding of Chinese, translate it into Chinese and pass it on to the other side, this says, well, this person maybe can perform this task but not necessarily understand what's happening and doesn't have any working knowledge of the language. Then there are also two types of mental models that you may want to aim to satisfy when you do explain. So one is a functional mental model, where it is just about understanding the process. And what I mean is, if you have a concept, you know how to operationalize it. And a great example of that is a light switch. So we all know how a light switch operates. You want to have some light in your room, you flip a switch, and then a light bulb turns on. That's great, we all know how it works. And this is functional understanding of this phenomenon. But then there is more in-depth mechanism happening there, which is structural. So a structural knowledge can be a wide range of topics. And this spans from just understanding how electricity works in physics, but it may also involve actually understanding how the energy is generated, where it comes from, and what happens when you flip that switch. But these are very conceptual ideas, so let's try to be a bit more precise. And we thought about it long and hard, and this is what we came up with. We said, well, explainability is not some arbitrary concept. It has well-defined components and an objective. And the components that go into explainability is transparency. So you have some process. And in order to explain it or to understand it, you need to get some insights about this concept. Then you may also need some background knowledge about the phenomenon that's happening. And this can be in any level of difficulty. It can be very basic understanding or very in-depth understanding. And on top of that, you need to process this information, you need to combine it. And this is where the reasoning comes. And once you reason about the insights given your background knowledge, you have an explanation. And an explanation is not just put out there for people to take. You should worry about what's happening with it. And it should lead to an understanding. And it's always aimed at somebody. At least it should be aimed at somebody. So let me give you a quick example. If you look at the top here, say that these are your explanations, and there's a black box that decides whether you like or dislike the weather today. And it says, here are exemplars, these are your explanations. Well, they don't tell you much unless you apply reasoning. And in this case, it's a human who reasons about it and extracts the explanation. So I say, oh, well, the temperature and rain does not change. It only depends on the humidity. So if the temperature is 23 degrees and it's not raining, the humidity decides whether I like or dislike the weather. This is fairly straightforward. So we could possibly outsource this task to a machine. Then it may become a bit more complex. For example, if you have logical rules instead of exemplars, you need to apply a bit more reasoning, say, oh, well, okay, so rain doesn't really matter. Humidity, the only thing that it has in common is the medium humidity, and then it differs in the temperature. So if I apply this reasoning chain, I can say, well, if it's not raining and the humidity is medium, if the temperature is between 12 and 22 degrees, I like the weather. And if it's above that, I dislike the weather. So reasoning is very important, and it can be either done by a human or by a machine. And this is not a new concept. And Tim Miller, who published this great paper, actually argues for more insights from social sciences and social science research on human explainability into XAI. And I really can recommend this paper if you haven't read it yet. And it has a lot of great findings, insights from social sciences. But the two most important ones, at least for us, is that explainability should be interactive. You should not expect to give the explainee just one explanation, regardless whether it's a patient of a doctor or a medical student or a medical colleague, and expect them to be happy with it. It needs to be a dialogue. Maybe the person doesn't understand it. Maybe you need to lower the level of complexity of your explanation or change something. Or maybe you're explaining the completely wrong thing and they're interested in something else. And also humans tend to explain in contrastive statements. What you have observed on the previous slide, what I was looking for while reasoning about the exemplars and the logical rules, I was trying to find something that could allow me to distinguish between liking and disliking the weather. So this is general about explainability, and it applies to, I would say, any sort of explainability, not necessarily only surrogates. But let's move on and let's talk about surrogates, because this is the main topic of this hands-on tutorial. So I'll talk briefly about surrogates as a general concept, and then we'll dive into text, image, and tabular data in that order. So surrogate is something that, a transparent model that mimics an opaque process that you want to explain. So there is some very complex opaque process. You may not understand it because it's too complex for your level of understanding, or it may generally be too complex for any human to comprehend. So there are different types of black boxes, but the basic idea is that you don't understand what's happening there. So then you can build a surrogate that mimics its behavior and is transparent enough for you to understand. So one way to do it is to have a global surrogate where you're trying to mimic the whole decisive process. You just want to know what's happening in general. Then you can have a local surrogate. So you don't care about the whole behavior of the black box. You just want to know what happens for a specific, say, prediction in machine learning, or a cohort. So a group of data points that share the same characteristic. Like, for example, people of age between 20 and 29. So that was the scope of the surrogate. Then we also have the source of mimicry. This is not a popular concept in machine learning, and I'll show you the more popular one in a moment. But imagine here that when you build a surrogate, you don't want to just observe its behavior. You actually dive into the technical details of it, the mechanics of the black box, and extract a bit of it that is simple enough and concise enough to serve as an explanation. And I think a good example of it is, so say with the previous one that I mentioned, if you have a decision tree that with the top node splitting on age, and you're only interested in, to the left you have people that are less than 20, and to the right you have people that are older than 20. Then if you just extract the subtree, the left subtree, you are explaining people that are younger than 20 years old, and you use the actual behavior of the model to explain it. You use the structure of the tree. Then you have behavioral surrogates, which is basically you do not care about what's happening inside the black box. You just observe how it behaves and try to replicate that process. So where does it fit in machine learning explainability? Well, you have a black box, and then you put on top of that a surrogate explainer, which is usually a local and behavioral surrogate, which produces an explanation and which is then delivered to a human explainee. And to ground this idea, this is one of the figures taken from the line paper. And here you have the background, which is the blue and red shading, your black box that you're trying to explain. These are the instances that help you to fit a local surrogate. The surrogate in this case is the linear model separating the two classes. And then you can explain this particular neighborhood without any regard for the complex behavior of all the other nooks and crannies of this black box model. And well, while this is very appealing visually, it actually is not how line for tabular data operates, because there is one component missing, which is the interpretable representation. And hopefully by the end of this talk, you will understand, if this is how you understood by now how line for tabular data operates, hopefully you will correct that by the end of the talk. So why do people love surrogates? Well, because they are plug and play. They are model agnostic, which means regardless of what sort of black box you're using, you can fit it there. They are post hoc, which means if you have a pre-existing black box, you can retrofit it into your system without changing anything to the pipeline. And they are also data universal. So I've already mentioned the concept of interpretable data representation. And it allows basically to reuse the same idea of a surrogate for image, tabular, and text data. There are some popular surrogates, which many of you probably are familiar with and maybe even have used. The top three, so LIME, Anchor, and SHAP, are both model agnostic, post hoc, and data universal, whereas RuleFit, which is much older, is just model agnostic and post hoc. It is specific to tabular data, but hopefully by the end of the talk, you will have an idea how to adapt it to images and text. So it seems like, you know, the silver bullet, you can solve any opaqueness problem in machine learning with surrogates. Well, if that was the case, we probably would be done by now. Sorry to disappoint you. There is this folklore in computer science called the no free lunch theorem, which in this case can be understood as a single explainer cannot perform universally well across all the possible explainability tasks, which means if something seems like it works with everything, it actually, no, physically it fits. You can generate an explanation, but you should not expect the same quality of explanation for every single problem that you apply a surrogate to. So how does it work in explainability? Well, there is this great paper from Cynthia Rudin where she argues that we should not really use post hoc explainers, which are the ones that are retrofitted into pre-existing systems. Instead, we should invest time and design explainable machine learning. And the main problem with post hoc explainers is that they have poor fidelity. And what is fidelity? It's basically how well your surrogate is able to mimic the black box. And because it's a one-size-fits-all approach, usually it's not that good. And the argument goes, well, in data science, we have all these frameworks to actually design predictive pipelines like KDD, CRISP-DM, and big data. And we need them in order to build good predictive pipelines. So why do we expect that there's this magical thing in explainability that would solve all of our problems? Instead, we should focus more on building informative features and training inherently transparent models. But this is hard, it requires effort. And surrogate explainers, as any other post explainer, is just easy. You have this magical thing, you just put it at the end of your predictive pipeline, and it spits out explanations. Well, so what we need probably is a process for explainable AI. But because the field is still fairly young and quite rapidly developing, we can't at the moment create a process like it. There are some attempts, like we, for example, created an explainable AI taxonomy, and there are other works that discovered the concept of building a framework. So here is the example of both. In the taxonomy, we touch upon 5 different dimensions: functional, operational, usability, safety, and validation, which allow you to assess your explainer against a set of desiderata and check whether you need to tweak it somehow, whether it is sufficient. It basically forces you to work through sort of a worksheet and understand what your explainer does and whether it's sufficient for the use case that you're trying to deploy it in. Whereas the generic framework for black box explainers approached it from more technical side and said, well, most of the explainers have 2 components. One is data sampling, and the other one is explanation generation. And once you do that, back and forth, you generate an explanation. There is an explainee to whom you deliver the explanation, and they show that you can fit a lot of explainers into that framework. But then we said, so it's not possible to do it for an XAI as a whole field, but we can do it for surrogates. And we thought about it, and we came up with bLIMEy, which stands for Build Lime Yourself. And it's a generic framework for building surrogate explainers. It also has a meta algorithm for doing so. And it is accompanied by a lot of analysis of the surrogate building blocks for different data types, as well as practical recommendations, which we'll go through in this talk. And what it means is that with bLIMEy, you can actually build a flexible, faithful, interactive surrogate that quite possibly does not suffer from low fidelity, but there is a catch. And the catch is as usual, it requires effort. You can't expect to have one explainer and then fit it into whatever problem you come across and expect it to work equally well. So what is bLIMEy? The original idea was, well, we have these 2 components that you've already seen, data sampling and explanation generation. But then there's a third component, which is really important, and that's the interpretable data representation. It allows you to approach different data types with the same sort of explainer. And then at the end, you obviously need to validate it because you want high fidelity. We tried it out and we thought, well, it doesn't really work that well. So what was the problem? The problem is that because there are so many components and they have so many parameters and you can choose and mix and match, that you actually should validate each component independently as you go, just to make sure that it fits. And this is what the rest of this talk is about, how to actually do that for tabular image and text data. And also then it's followed on by the hands-on part, which will try to instruct you how to do it in practice. And yeah, hopefully by the end of the tutorial, you will understand why this image should not be taken in its face value. Right, so let's dive in and let's have a look at how some of the surrogates work. And we'll start with text, because text is pretty straightforward. So where we start, we start with a data point. In this case, it is a sentence. And the sentence says this sentence has a positive sentiment, maybe. We feed it through a black box and we get a prediction. The prediction is it's either a positive sentiment or it's a negative sentiment. In this case, the black box says it has a positive sentiment. Where do we go from here? Well, we start with the interpretable data representation. And what happens here is we need to find how to represent a sentence like this to make sure it's understandable to humans. And a very straightforward approach to this is just use bag of words. You split the sentence on white spaces, and then you treat each individual word as an interpretable feature. then this sentence is such an interpretable representation is shown as a binary vector where 1 indicates presence of a given token and 0 would indicate its absence, and we'll see that in a moment. But let's discuss this concept of interpretable data representation for text a bit more. You may be wondering, well, there are a lot of words that are not really important for humans to understand text. And if I get rid of these words, you'd still probably make sense of the sentence. And you can reflect that in your interpretable representation. So what you can do, you can discard stop words and punctuation. And this has two benefits. First of all, we only focus on information that is important for the prediction, at least from our perspective. And then you also reduce the size of your interpretable data representation, which is good for the explainee because you do not overwhelm him or her. But we can take it a step further. So you may say, well, I may want something more complex, in which case this is obviously possible. You can merge different words if they make semantic sense to people. So in this case, I represent both these words, sentence and sentiment, as a single token in the interpretable data representation. And if you go this route, there is a wealth of literature on natural language processing that has plenty of inspiration how to design interpretable representations that will work well for your particular case. So if you do work with text, I encourage you to focus on designing a proper interpretable data representation. So once we have that, what's next? Well, data sampling. It's not really possible to sample directly from text just because it's an ill-defined procedure. How do you do that? But fortunately, we have the interpretable data representation. So what we do, we just say, well, we have vectors of length, binary vectors of length 4, and let's just replace random, let's just place random 1 or 0 at every component, and that's our sampling procedure. Great, so we have this sample in the interpretable representation. What's next? We go for the explanation generation step. And the first procedure here is we need to analyze the behavior of the black box for our sample, but we can't do that with the binary vectors. So we need to restore them to the original representation. And fortunately for text, this is pretty straightforward. When you set a parameter to 0 in an interpretable vector, you basically erase a word. That's very natural to how humans comprehend text. If you want to remove any information from a sentence, you take a chunk out of it and then present it. That's basically how censorship works, actually. So you may think of it as censoring your sentences. Once you remove bits and pieces of information, you want to understand how black box responds to these edits. So you feed them through your black box and you get prediction again. In this case, this is just a binary black box. And as you may have noticed, when we sample the data, this is implicitly local sample, which means it only applies to our sentence that we're trying to explain. It cannot be generalized to other sentences. And you will observe the same behavior in images, but this breaks apart in tabular data, which is part of the problem. So next, let's say that you want to favor edits that are very short. So if you just remove a single word as opposed to 5 or 6 words, you want these data points to be more important for generating your prediction than sentences that say are left with only a single word, or like here, or 2 words. And you do that by first measuring a distance. Obviously, the choice of a distance, it's up to you. You need to decide what works, but possibly for text, edit distance is the best. And then you change this distance into similarity by using a kernel. So you kernelize the distance and you get a similarity score, which you use to weight your binary data points. And where it comes to play is we have all of the components, we generated them. So how do we get an explanation out of it? We feed a local surrogate. So for the data to feed the surrogate, we use our binary sample. Then we weight these instances by the kernelized distances. And for the predictions, for for when we fit the surrogate. We use either 0 if it's a negative sentiment, or positive if it's, or 1 if it's positive sentiment, because this is the class that we're trying to explain. Then we fit such a sparse linear model, we extract its coefficients, and because all of the features are within the same range, 0 and 1, they are comparable, and we can plot them like this, like a bar plot, and interpret how each word or token, or however you organize your interpretable representation, casts a vote for the positive sentiment. Well, you may think I can't remember what F1 is, F2 or F0. Fortunately for text, you can represent it, you can overlay it on top of your sentence, which means that if you were able to comprehend the original data point that you are trying to explain, there is no need to alter it in any way. You can still comprehend the explanation by just coloring it or showing the importance next to every single word. Well, so far so good. This was, I hope, pretty straightforward. Let's see what happens for image data. It is not too different, although there are a few caveats that you need to be aware of. So same situation, we have a data point, an image of a dog, and then we have a black box classifier that predicts between Husky, Eskimo, and Malamute dog breeds. And in this case, our black box predicts a Husky. So this is a slight complication over the previous example where we only had binary predictions, and you will see where this comes to play later on. So what's an interpretable data representation for images? For images, we simply partition them into non-overlapping segments called superpixels, and then we annotate each partition of an image as our interpretable feature. And again, the original image is represented as an all-one vector, which means all of the superpixels are preserved. You can apply the same strategy as with text data, which means you can get creative with your interpretable representation. So for example, here, in order to reduce the dimensionality of my interpretable representation, I merged all of the top 3 segments, which is the grassy background. And then I merged the 2 on the right and the 2 on the left, which are the snowy backgrounds, which first of all gives you more semantic meaning to your interpretable data representation. And let's be honest, this is how you express your explanation. This is how you present it to the explainees. So you want it to be conceptually sound. And also, secondly, you reduce the dimensionality. So what happens next? Again, very similar to text, the procedure of sampling data from the original domain, which are pixel values, is ill-defined. So instead we go for the interpretable domain, and we sample the vectors of the same length as the number of our interpretable features. And these are binary numbers. Next, how do we remove information? In text, this was pretty straightforward. We just removed a word from a sentence, and the model could handle it. And this is because text model, natural language models, are very flexible and they do not assume a fixed input size. Whereas for images, this is the case. You need to preserve the original image structure, and there's no easy way to remove. So what's the next best thing, a proxy to remove information from an image? Yeah, this is what we show here. You just occlude it with some sort of, here, for example, a black patch of color. But there's a problem with it. We made an arbitrary assumption here that black color is not important for any of the classes that the black box predicts. And you can see it here. For example, if I use black occlusion, my black box model outputs Malamute, whereas if I use mean color occlusion, which is calculating the mean pixel value for a patch, and then replacing this patch with this particular color, it gives a completely different prediction. And obviously, since we use these predictions of our black box for the modified images to fit our surrogate, this may have an adverse effect on the quality of our explanations. By the way, the one on the right, the mean color occlusion, it is how bLIMEy handles image data. So we thought, well, if it affects the predictions of the black box, can we actually measure the effect? Yes, we can. And we studied how did the occlusion color and the segmentation granularity, so how many segments you split your image into, affect the black box predictions. So on the x-axis here, you see the number of segments. So here from 0 to 5, number of segments that were occluded. So 0 segments, you have 0 error on the image. So this is an error with respect to the biggest, the top class predicted by our probabilistic black box. And as we occlude more segments, you can see that the error raises, which is expected. You remove information from your image, so the error is bigger. And different lines represent different occlusion colors. And as you can see here, for 5 segments, the pink line, which represents the pink line represents the mean color occlusion. You can see that it slightly diverges, but it's not too bad. But once you segment it into 40 segments, it is actually quite a substantial difference. If it lowers, it means that the black box is more likely to still predict the original class that was predicted without any occlusions than if it's higher. And why this may be happening, let me give you some intuition. As you start splitting images into more and more segments, the segments become smaller, and their color diversity is also smaller, which means that if you occlude them, if you have enough segments and you occlude them with their mean color, what you're effectively doing, you're just blurring the image. You're not removing any information. So one takeaway from this is, if you have a lot of segments, do not use mean color occlusion, because you're effectively not hiding any information from the black box. Well, so what happens next? We already know that we shouldn't use the mean color occlusion. We come back to predictions. We reverse our samples from binary into the original domain. We predict them with our black box. Then we follow a similar procedure. We can use a distance metric to favor images that have smaller number of superpixels occluded and weight them appropriately. And we generate the explanation. And in this case, so in case of text, the explanation was importance of a word or a token for a given prediction, for predicting the positive sentiment. And here, this is an importance for a class. You can, before we define what class we're describing here, let's have a look at the different representations. So similar to text, you don't need to plot it as a bar plot. You can overlay the explanation on top of the image and highlight the regions that are important and the regions that are not important and annotate them. So why did I say that we're not quite sure what class we're explaining? Well, that's because our model is not binary. So there's an implicit one versus rest problem to address here. If your black box predicts 3 classes and you're explaining just a single one, and let's say that your black box is a crisp classifier, then you need to select which class you're explaining and then code the predictions of your black box appropriately. So if we're explaining husky, we assign 1 to husky predictions and 0 to any other. So whether it's an Eskimo dog or a Malamute, we assign 0 because we're not interested in this class. And in this case, the predictions are with respect to husky. Right, so what happens if we have a probabilistic multi-class classifier? Well, then instead of using a linear classifier, we use a linear regressor. And if we want to explain husky, we don't need to change anything. We just extract a single column and fit our surrogate regression into this column. Well, there is a problem with that. If you look at these 2 rows, they are quite different, yet you still encode them as with just a single vector of probability. So what happens, you can see that for this row, husky is predicted with 88%, and for this one, it's 58. So here, the probability mass dominates the husky class, whereas here, it's almost equally distributed among the other 2. So what you're losing by following this approach is you're just saying, I don't care whether it's Malamute or Eskimo, I only care about husky. But you also don't really care how much of a husky is it. And there, fortunately, so you could treat that as, you could possibly get argmax and just do, yeah, let's forget about probabilities. We'll just use the top predicted class. But then you're losing important information. You can only ask, why is it a husky and not anything else? But maybe you're interested directly in the difference between, say, husky and a Malamute. And this sort of a surrogate will not be able to answer that question. There is a trick that you can use. And there is a class of models called multi-output regression. And the hands-on materials will focus on trees, but you can use it with any other surrogate model as long as it supports multi-output property. So what happens here is you say, well, I want to explain these two classes, and then you extract these two vectors, and you fit the regression surrogate to both of them simultaneously. You can have a look at this paper. It provides more details on this approach. And what this basically allows you to do, you can say, well, why is it a husky and not an Eskimo? Why is it a husky and not a Malamute? Instead of just asking, why is it a husky and not anything else? And also, it will allow you to track the exact probability mass. So, you will know that it's only, say, 64% probability as opposed to 99. So this is a very interesting concept that if you want to understand a particular difference between two classes, which is coherent with Tim Miller's finding that explanations should be contrastive, this is where you should go. Well, so far so good. We've covered both text and text and image. For text, it was pretty straightforward. For images, we had a problem with occlusion color and the granularity of the segmentation, as well as deciding how to feed a surrogate, whether it should be a classifier, a regressor, or a multi-output regressor. Let's see what happens for tabular data. This is by far the most interesting case because it's also the most complicated one. So again, we start with a simple toy example. We have a two-dimensional dataset for the purposes of visualization. And we have a black box that decides whether it's a red or a gray class. And the explained data point is 0208, and it's the green star here. So what's our interpretable representation in this case? Well, you may think, let's go for a binary. Is it 0.2 on the x-axis? Is it 0.8 on the y-axis? If it's exactly the same point, our binary interpretable representation would be 1, 1. If it's anywhere else, it is 0, 0. Well, this is not really how we think usually. So for example, it may be the case that you're trying to predict. So, it's very diverse. And assuming that the remainder of the decision space is 0, 0, whereas this is just 1, 1, the horizontal line would be 1, 0, the vertical line would be 0, 1. You lose a lot of information. So can we do better? Yes, we can. And we approach that by discretization. So if you have categorical features, you leave them alone. You don't need to do anything. But for numerical features, the first step of your interpretable representation is to discretize them into how many ever bins you want. In this case, we use quartile discretization, which means we split each feature into 4 bins. And then we encode them in the intermediate representation. Remember that this is just the first step of our interpretable representation as this bin. So this bin is 0, 0, this is 1, 0, 2, 0, 3, 0, etc. Our explained data point lies in 3, 0, in 0, 3. And this is how we encode it in this representation. That's great, but this is not binary. We need to have binary concepts that we need to switch on and off. So how do we follow that? Well, we basically say very similar to what I explained with just taking the data point. We say, well, if it's in the same quadrant as the explained instance, on the x-axis, we say it's 1. If it's on the same quadrant on the y-axis as the explained instance, we put 1 in that direction as well. So here, because it's on the same partition of y as the explained instance, but it's not on the same partition, x partition, we put 0, 1. Here 1, 0 for the same reason. And this is all merged together as 0, 0, so this is offline. There is a problem with this though. So once you discretize, you basically create a lot of discrete partitions, and they grow exponentially. So basically you have the number of splits on each axis to the number of original dimensions. So for our case, for example, we had 16 hyperrectangles in the discrete representation. But then, fortunately, you reduce them to just 2 to the number of dimensions once you binarize. So just to give you an example, with 11 features, there would be more than 4 million hyper rectangles in the discrete space and about 2,000 with the binary, which means if you want to cover each hyperrectangle in the discrete, you would need to sample 4 million data points. Well, that's a lot. And there's also another problem with this sort of interpretable representation. So once you go via these stages, what you are trying to capture is the behavior of your black box. This is what you're explaining. So imagine that this is not our data set, that this is a sample around our explained instance. Then we discretize it. And in this case, we're quite fortunate because if you look closely at the hyperrectangles, they're quite clean cut. So we kind of expect that the black box decision boundary would be running something like that. And they pretty much approximate it. But once you go into the binary representation that we need for the actual explanation generation, we start merging these hyperrectangles and we may lose a lot of information. In this case, it's not that bad. We just mix this one red bit with the gray moon, but it can get much worse than that. Here, we are fortunate enough, these are 2 dimensions. We can easily visualize it and inspect it. But what do you do in the higher dimensions? Well, we thought about it and we say, what we care about is actually the purity of each partition. So what it tells you, if these dots are predictions of our black box, if a hyperrectangle is pure, it means that the black box decision boundary does not run across it. But then if you see here, there are not a lot of data points in this hyperrectangle and not a lot of data points here, but the rest have quite a lot. So how do we combine that? Well, we take a weighted average and we use the number of data points in each hyperrectangle as a weight. And what this allows us to do, it allows us to compute for crisp classification Gini index or Gini impurity, which tells us how well does our discretization capture the black box decision boundary. And for probabilistic classification or regression, when you fit a surrogate to these 2 types of models, you calculate the mean squared error to understand whether it's pure or not. So if it's pure, it's good. You want pure discretization, it means that, or binarization, it means that you're capturing the characteristics of your black box decision boundary. If it's not pure, well, you're in trouble and you probably should work a bit harder. So this was quartile-based interpretable representation, the one used by bLIMEy, followed by binarization. There are alternatives, and one alternative is to fit a local tree. So you don't use tree, at least not for now, as a surrogate, but you use it to create a data space partition. And in this case, I restricted the number of leaves in the tree to 4. But you could possibly have as expressive tree as possible to capture this small bit as well. And why did I do that? Well, if we want to be fair and we want to compare this interpretable representation with the quartile-based one, we need to binarize it. And binarization in this case is just one-hot encoding. So we create a binary vector of the same length as the number of hyperrectangles, and we can give each one a unique binary encoding. In this case, we just have 4 encodings, which is directly comparable with the binary interpretable representation based on quartiles. Okay, so this was the interpretable representation. What happens next? We need to sample data. And how we sample data, well, we have a choice again. We can either do that in the binary domain, and this is pretty straightforward. We follow a similar procedure to image and text. We just get binary numbers and assign a data point. For quartiles, this is almost the same. Instead of sampling from 0s and 1s, you sample from 0 to 3 inclusive. And then it assigns the data point to a hyperrectangle. And then finally, you can sample from the original data domain. So let's explore it a bit more. For binary sampling, if you only have information ones and zeros, they can only tell you whether you're in the blue and yellow region, just blue, just yellow, or without any background. This is all the information you get. How does it look like for the intermediate discrete representation? Well, you get a bit more granularity. Instead of just these belts, you actually know, well, it's either in this hyperrectangle, somewhere in this hyperrectangle, here, somewhere in this hyperrectangle. We'll discuss that in a moment, but next, let's have a look what happens when we sample in the original data domain. There are a lot of sampling approaches that you can use, and two very popular ones for surrogates are normal sampling. So you just fit you sample from the Gaussian fitted around your explain data instance, or you use truncated Gaussian, which makes sure that your data points do not go beyond the minimum and maximum of the underlying data set. But can we improve on that? Yes, we can. And we do that by taking into consideration the label of each instance. So coming back to this example, these are not good samples, and they are not good because you do not discover the black box decision boundary. You only get 4 points of the opposite class here, or here 5. So we need something that allows us to discover the black box decision boundary. And there are two approaches, one which we authored called class discovery, which actually forces discovering different classes, and another one called mixup. Both of them consider the label of our instances and make sure that we have a diverse sample. And like I said, a diverse sample is needed because you want to approximate the decision boundary. If you have a diverse sample, it means you hit the black box decision boundary and you can approximate it with your surrogate. So in the case of interpretable representations, we wanted to have as pure partitions as possible. Here it's the completely opposite. You want to have as diverse sample as possible because it means that you're in an interesting region, in a region where your black box is uncertain. So the region that is worth explaining. But let's come back to these weird sampling approaches from your binary and discrete domains. So like I said, you only get an information about which hyperrectangle the point should belong to, but you don't really know what's the exact point. And as you recall from images and text, we need that because we need to predict these instances with our black box, this sample, our augmented data, in order to capture how the black box behaves in that region. And what the only opportunity here to do that is to fit some sort of distribution to the data points that would have been there from your training data. And then once you know, oh, well, it's in this hyperrectangle, so I will just sample from this fitted distribution fitted to the hyperrectangle and use this as my explain instance. And you can see an example of this here. So for each hyperrectangle, we just fitted a Gaussian distribution and sampled a point from there in order to recover. There is a trade-off here. So if you use sampling from either binary or discrete, you are kind of guaranteed to have a diverse sample because you're sampling from hyperrectangles. They may not be close to your explain instance, but this can be addressed with weighting. But what happens is the actual sample is not really local, it is global. And also you introduce randomness because you need to fit this Gaussian distribution in order to recover your points. Well, the trade-off is that you can use, instead of sampling from these two domains, you can sample from the original data domain, but then you need to make sure that your algorithm is first of all explicitly local, so it will only give you a local sample, and second of all that it discovers diverse classes. And also you don't need such a big sample because I remember the horrendous numbers for the number of hyperrectangles in high dimensions. This does not really apply, this does not hurt that badly for sampling in the original domain. So if you do decide to go this way, and by the way, this is how bLIMEy operates, you probably need to introduce some sort of locality. And this is where data weighting comes in. So first you calculate the distance. And again, there is a choice. You can calculate your distance in the binary domain, in the discrete domain, or in the original domain. and there are different behaviors. You will be able to explore this in the hands-on material. There's quite a lot of plots there and code that shows you how this behaves in different scenarios. But then you need to kernelize. Distances are not enough. And then the question is, well, so first of all, what sort of distance you use, and second of all, which domain you compute this metric in, and then what sort of kernel you use and how you parameterize your kernel. And this is very sensitive for the quality and accuracy of your explanation, as you can see, because the samples are quite diverse. And you will have an opportunity to explore that a bit further in the hands-on part. Well, so what happens next? We have all of these components, and if we generate an explanation, we may run into troubles, because as opposed to images and text, where we could actually overlay the explanation on top of the explained instance, and we didn't have that much troubles visualizing it, because if we were able to comprehend the explained data instance, we also are able to comprehend the explanation. This is not necessarily the case for tabular data, where we can only use bar plots to express our explanations. And this is where feature selections come in. So in order to not overwhelm the explainee and reduce the number of important factors that you're trying to present as the argument for a particular class, you need to reduce the number of interpretable features. And there are various approaches such as lasso path, forward selection, and highest weight. And we also explore these in the hands-on material. Right, so let's have a look at the actual explanations, because I promised that by the end of the talk, you will know how to interpret LIME explanations. So this is a linear surrogate based on discretization and binarisation. And this is very close to how the actual LIME for tabular data operates. So what happens, you have this binary concepts, and binary concepts in this case for the x is x1 between 0.3 and 0.47, and x2 between 0.54 and 0.67. So 1 in these dimensions mean that we are somewhere in the yellow belt. 1 in these dimensions for the interpretable representation means that we are in the blue belt. 1, 1 means that we are dead center in the hyperrectangle that the explained instance lies. And 0, 0 means that we are somewhere in the not colored region. So what it tells you, it tells us, well, for the second feature, so here, the yellow belt, it is important, this belt is important for predicting the red class. How to interpret that? Well, you need to remember that linear models assume feature independence. And where it comes to play is, if you have a look at what sort of points we have at the top and at the bottom, you see that there are only a few red points here and a lot of gray points here. So what the explanation tells us is that if we move outside of this region, so from blue and yellow into only blue, we are more likely to predict gray than we are likely to predict red. So for red, staying in this region, it is important. You may be a bit surprised because there is red on top, but remember that there in the interpretable domain, in the binary interpretable domain, there is no difference between the top and the bottom. They are both encoded as, this would be 1, 0. So this is 1, 0, this is 1, 0, this is 1, 1. And then for the first feature, so for the X one, it says it is negatively important for the red class. And the reason is that if you have a look and apply the same reasoning, in this belt, there's only a few gray points and a lot of red points. So it doesn't really matter whether you're out or in, because you're very likely to predict red. And this is basically a consequence of using a linear model, which assumes feature independence and linearity. And linearity is very important, by the way, for images, because superpixels that are next to each other are highly correlated because images are a continuous space. And you can observe that. And if you have a look at any of the papers that we link here, there is quite strong evidence for that, which also suggests that you should not really use linear models as your surrogates. So let's have a look at the different thing. And this is very close to what rule fit does. So what we do, we fit a linear model, a decision tree into our sample. And then we extract rules for each of the partitions that the tree learns, and we one-hot encode them. And we fit, again, a linear model into this one-hot encoding. You've seen that before in the slides, and you will also see that in the hands-on materials. So then the rule fit-esque explanation, let's call it like that, says that if you're above 0.55 on the y-axis, you're very likely to predict red, which is, I mean, it's reasonable. It's mostly red. But then if you're below the 0.55 line, if you're to the right, it's a negative for red because it's mostly occupied by gray class. And if you're to the left here, you're very strongly, it's strong explanation for the red class because this is mostly red. It's very intuitive. So this basically shows you that you can also fit a rule fit explainer into this surrogate framework. So the final one is a tree-based explanation. So instead of playing with one-hot encoding your features and then fitting a linear model, you go straight with a decision tree. Decision trees give you by default feature importance as an explanation, but keep in mind that this is a global explanation. It is not with respect to any single class. And then you can also visualize the tree structure itself. And if we go back to the very first slide when I said, well, an explanation requires reasoning, this is where all fun happens because you can do counterfactuals. If you say, oh, you know, I'm above 0.55 and I'm predicting red, what can I do to change my prediction to gray? And then the tree tells you, well, you just need to go below 0.55 on the y-axis, and then you're more likely to predict gray. There are 78 gray instances in comparison to 41 red instances. You could do a similar reasoning here. Well, if I'm in this quadrant, how can I be from red get gray? Well, you just need to move to the right, and then you'll predict gray. So you move from here to here. Well, this is very simplistic, but once you have multiple classes, either it's a crisp decision tree or it is a multi-output regression tree, it becomes quite a powerful explainer. And if you process the tree structure algorithmically, as opposed to visually inspecting it, you can generate a bunch of useful explanations. And that pretty much sums up tabular surrogates. Well, by now, you probably would have hoped that I'll give you a magic formula for building surrogates. I'm sorry to disappoint you. It's not that easy. As you've seen, there are a lot of components, a lot of parameters. You need to inspect and measure each step, make sure that it works for your case. And it basically requires work. As Cynthia Rudin has argued, we should start building explainable models as opposed to use one-size-fits-all surrogates or post-hoc explainers. I would say that, I would add to that and say, well, you can use post-hoc and surrogates as long as you also work on them and make sure that they are useful and good for your particular case. Right, I hope that was reasonably clear and that you are well prepared for the hands-on session. But before that, I'll hand over to Alex, who will introduce you to our interpretability tools and then tell you how you can get hold of the notebooks, etc.
Thank you, Kacper. That's really helpful. There was a question here that I think might be interesting to briefly address from
Sure.
From Richard Leibrand, who says, I fear the following. My users will not understand how the surrogate works, maybe for tabular data in particular. Thus, they will not really understand what the numbers mean. Thus, they will not trust the explainer more than the original black box model. How would you respond to that?
Well, it depends how you produce the explanation. So first of all, you need to know the background knowledge of the explainees. And as I said with the example here, so the LIME explanations, the pure LIME explanations, understanding how actually how it operates in the binarized domain, I can agree that this is quite tricky and it takes quite a while to grasp this concept. But once you move to trees, and instead of saying, well, it depends on how you build the interpretable representation and how you need to keep in mind that the linear models have feature independence assumption. Once you move here, there is not a lot of assumptions. And if you process the tree structure algorithmically and extract counterfactuals, the users or explainees do not really need to understand what's happening. You just say, well, you're here, move to the right, and that's it. So it very much depends on who your users are and how you deliver the explanation and who does the reasoning. So in the case of this talk, I did all of the reasoning. I showed you building blocks. I kind of mimicked it. But at the end, you need to decide whether it's the users who do all the reasoning, or you do part of the reasoning on the algorithmic side. Or for example, maybe you want to provide a training beforehand. You gather people, you say, this is the explainer that we use, this is how we interpret it. Then you enrich their background knowledge, and they may be able to do that by, in their minds, as opposed to you doing it algorithmically.
Okay, thank you. Let's now move on to Alex. I think we have half an hour and then we have a break. Is that right?
Yes, that's correct.
Okay,